All right, we are live. This is the third last lecture of this course. Feels kind of crazy. And it is the last lecture where I'll be here in person. So the next week I'll be away and one of the TAs will be here and project me on the screen. I guess they'll just project the Google Meets call. And yeah, and then if you want to ask questions, you can still ask and then I'll answer them. But you can come to the class and if you want to still watch the lecture. I know last year I had to miss like 2 lectures and students thought this was useful, so we'll do it again this year. Yeah, so this will be the last time you see me in person, I guess, other than the final exam. And so let's see what we're doing today. So we're just gonna spend maybe 10 minutes to clean up and clarify a couple things for this multi-class classification business. And then we'll spend the rest of the class talking about neural networks. And for that lecture, I posted some notes with a lot of pre-filled in things because I realized that it's unlikely I'll cover it if I have to draw and write everything in class, but I want to cover it all. So yeah, there's like the notes on the website that are like half pre-filled in with a bunch of pictures and stuff. Okay, and we'll use those and we'll fill in things live. Okay, so let's just remind ourselves what happened in this whole classification business. So classification was this setting where the labels are some discrete set of like unordered objects. You should think of them as like pictures of cats, dogs, elephants, things, and so on. And then we represent them as numbers, natural numbers, such as like 0, 1, 2, 3, up to k minus 1. So if you have k objects you want to talk about, you represent them as numbers from 0 to k minus 1. And then we said we want to predict what is the correct label given some new feature, which would be like you're given a new photo, what is the thing in the photo? And we found that the kind of optimal way to do this was actually just to, well, if you knew the probability of the corresponding label y for the given photo, you should just pick the corresponding label that has the highest probability. Okay. And then we spent a lot of time trying to figure out how we would estimate this object if you had multiple classes, which was last class. Multi-class means that there's multiple classes, and in particular, multi-class means that only one of the classes is correct. So that means that you have a photo where there's a single thing in that photo that should be labeled. There is another setting called multi-label classification, in which case there could be multiple correct labels. So you could have a photo with like a cat and a dog, which is not what we're dealing with here. Okay. And so yeah, coming back, really the whole difficulty was how do we estimate this PMF? How do we estimate the probabilities of each class so that we can just then select the one with the largest probability? And the procedure we used for that was maximum likelihood estimation. And that just looked like, well, we have this data set and we need to model or pick some assumption for what is this PMF? And what we chose is that it's a categorical distribution, which was without any loss of generality, because if you have k classes, you can describe any single PMF over these k classes by just saying what is the probability of each class. That's what this was here. The probability of each class or each label is just some parameter. The assumption was that the way this parameter is to be represented is through a softmax function. Okay, and that's the assumption we had. And the softmax function you should think of as, well, it's the following thing, but you should think of it's a way to take some number, well, actually a set of numbers or like a vector of numbers, and then make sure that it's a probability mass function, basically. So it will make sure all the numbers are between 0 and 1, and make sure that their sum equals to 1. So that's what you should think of this procedure as doing to the following k inputs. So you have these k linear functions. These can be any numbers between negative and positive infinity, and it just maps these numbers to numbers between 0 and 1 that will sum to 1. So it makes it a probability distribution. Okay, and that's good because that's what we need. These should all sum to 1, and they should be numbers between 0 and 1. And then all that was left was to figure out what should these weight vectors be. These weight vectors for these linear functions that then get plugged into the softmax. And then all we did was this whole MLE procedure, and I'm not going to go over the details, but the procedure was the same as we've seen many times, which is you write out the negative log likelihood, Now it's a function of all the weight vectors we have. We used to only have one, and now we have k. And then we just pick the weight vectors that minimize this negative log likelihood. Okay, so then we went over all the math to do that. And we got to calculating the derivative of this object inside the minimization problem. And what we found is this is the derivative. And unfortunately, there is no closed form solution, which means that if I try to set it to 0, I can't find some nice mathematical expression telling me what I should set the weights to. And so then we said, okay, another way to do this, which we know how to do, is to use gradient descent to get to something close to the minimum solution. And nicely, this function also is convex, the thing we were minimizing, due to the choice of this linear functions and the softmax. Turns out if you make these choices, it will end up with something convex. And what that means is when you minimize, you really do get to the global minimum. Okay, and we've seen this throughout the course. And a little, I guess, foreshadowing is that with neural networks, we'll see something different today. Okay. And so then you do gradient descent, and then if you do it enough times with a good enough step size, you will indeed reach something close to the maximum likelihood estimate of these weights. And those maximum likelihood of the weights will then be used as the estimate of this PMF. So now we return to how does the learner look? How do we actually predict things? Well, it's what we started with at the start of class, which is if I want to predict something, I need to calculate this PMF. Okay. How am I going to do that? I'm going to approximate it. That's where there's this approximately equal sign. And approximate it with this thing here, this PMF I just calculated by plugging in the maximum likelihood estimates for W. Recall that this function here above, this original PMF, was equal to the above with not MLE here, but with a star. Okay, so that was our assumption, that if you plug in W stars and you use the softmax function, then these are equal. And all we did was just got estimates of these things. And we plug them in, and that's why there's this approximate equal to sign. And in particular, this PMF took the form of this softmax here. And then the procedure was once you get this softmax function for each class Y, you just pick the one with the largest value, the one with the largest probability. And visually, it looked like this. If you had a bunch of, two features, then any point on this plot is a feature value, right? This would be like the point where x2 is very large and x1 is really small. And then you would be, okay, well, what class do I predict? Well, what you would do is you would plug it in to this equation here. You'd plug in your x into this type of equation. You'd get what is the corresponding value that gets output by this function. And you would look at that value for all the three classes in this case. And then the one that had the largest value would output. And in this case, it's probably would be good if your predictor outputted a label of 0 for probably a region like this purple region. And then similarly, a label of 2 for this region, a label of 1 for this. And this is indeed what the MLE solution will end up doing. And the point at which the prediction transitions, because it must at some, well, if it does transition, then you can draw a boundary at the transitioning point, and this is called the decision boundary. Rightfully so, it's the boundary at which you change your decision. Okay, and after that, that was the whole procedure. And then we also found out that people sometimes will call this procedure like softmax regression, similar to how we heard of logistic regression before. And that is just like another viewpoint of this as being some ERM problem that you're solving, or a regression problem you're solving with ERM. And in particular, the regression problem you should think of is that I need to calculate the probability of each class. That's a continuous number between 0 and 1. And so I end up with k regression problems. There's k labels, k classes. I just need to predict the value of each class. And I can do that with a regression problem. And then afterwards, I can do this extra procedure on top where I take the argmax afterwards. Okay, and so the way that is formulated as a regression problem is what is called this multi-output regression. So your set of labels is now this, not just numbers between 0 and 1. It's not this interval between 0 and 1, 0, 1 to the k. So there's k numbers. And the way and they represent the probabilities of each of the original k classes. And the way you encode your data into this format is that where you have a data point, which is just like a label, maybe like class 2 is what your first data point. The next data point is like class 0. Well, you encode the y's. These are what like your y will look like. This is y. It looks of this form. So you encode it as these what are called one-hot vectors. So it has just a 1 at the corresponding index of that label. So this is for class 1, or I guess the way we've been calling things, this is technically called class 0. This is class 1, and this is class 2. Okay, and then afterwards what we saw is that the loss, if we just go back up to what Emily was doing, we will find out that the thing it's minimizing is this thing, which is the negative log likelihood if you rearrange terms accordingly. And the predictor that is being used inside the log, you will find is a function that is the softmax. So you end up with a function class that's the set of softmax functions over different weight vectors. And the thing that I didn't have quite enough time to write, which is each one of these wi's, or maybe I'll write it as w's 0 vector up to wk minus 1, is an element of the usual rd plus 1. Okay, and that's the big set. And then ERM would simply compute the minimizer of this loss here, or the empirical risk. So you'd use this loss function with this function class. And if you write this out explicitly, you'll find out it's the exact same minimization problem we were solving in MLE, with the only difference being that this L hat has an extra 1 over n term in front, which is completely fine because that does not change the minimizer. Okay, and so you'll find that these are indeed the same. And then the last thing to have said was that you might wonder, like, what's going on? You know, we did this binary classification business, and then now we're doing multi-class classification. Okay, I had some notes here. Okay, maybe I'll say a couple more things. So, yeah, it's not that important, but this gradient, this was like the gradient we got for gradient descent. It had a very similar form to all the other gradients we saw, which is you have this like xij outside, and inside you have something like your predictor minus the corresponding label. And here the way this is viewed is this is like the probability of class y, and this gives you a 1 if the corresponding label is actually a y, and if it gives you 0 if the corresponding label is not y. And so, yeah, so this has a very similar form to something we've seen before. And okay, maybe that's all I want to say about that. So, oh, and another thing actually, I see now, is this thing here, just for terminology's sake. This thing is called sometimes just the cross entropy loss, or to make it clear from the binary one, it's called the multi-class cross entropy loss. So this is things you'll hear in machine learning world. Sometimes people will be like, okay, let's do, you know, classification using the cross entropy loss, okay? And then we'll use, yeah, the softmax function or something. And sometimes this is also called the log loss, because I guess it has a log. And if you look at the way this thing works, it's like only when your class, only when you match the class Q here, so only when y is equal to the index. So if you remember what y looks like these one-hot vectors. It only is equal to 1 at one index. So this thing will only, the sum will only have a non-zero value here for a single index. So in other words, you'll only suffer loss for your prediction, the log value, for a single index. And that's going to be the index for which this label is accordingly 1. So in other words, you end up only with loss based on what you predict for the corresponding correct class. And it's scaled as a logarithm. Okay. And then the final thing I want to mention was that we saw that, like, okay, softmax, like this multi-class setting, we can do, you know, different numbers of classes. And you might wonder, like, is softmax regression when k equals 2, so you have 2 classes, is that equal to logistic regression? Like, why did we have this separate case for binary classification? Isn't that kind of weird? And the answer is yes, they are indeed equal. And okay, so I'm not going to go over the details. It's like a little bit, quite a bit of math steps, I guess. So you can see the course notes for details. But what I did want to mention is the way this kind of works is what you will show is that in binary classification, or like in logistic regression, you end up kind of solving for this sigmoid, right? You get the sigmoid, and then you solve for this X transpose, and you solve for WMLE. And there was just like one weight vector here. And this thing represented the probability of class 1. And then to get the other probability, you just do 1 minus. And in multi-class classification or with softmax regression, to predict class 1, you had to use the softmax function with its first index. And then you would plug in X transpose. You would have a WMLE 0 for the 0th class. And then you would also have a X transpose WMLE for the first class. And it turns out that you can show that these are exactly equal. So in other words, this value you estimate of the probability of the first class is exactly equal to the same value estimate for binary classification. And that's just kind of rewriting the sigmoid function and the softmax, and you see that you just add and subtract some things, and they're the same thing. So then you end up actually minimizing the same thing, and so on. And so really, you never really needed logistic regression. You could just do the softmax thing to begin with, but people like to have this kind of simplified view with a sigmoid in the binary case and only predict one parameter. Okay, good. So that's the end of multi-class classification. Now let's get into neural networks. Okay, so how does this work? Well, the way it works is it's actually sort of simple given what we've already studied in this class, I hope. And that it fits into the framework rather nicely, and we just have to see what are the changes. So here's really the only change. We've covered, linear functions. So like we've had linear functions, which meant like, oh, this is what our function of x was. Then we had like the sigmoid function, that was another, choice for a predictor. Oh, there's no comma there. Well, you can come up with whatever functions you want, And turns out one other choice is what is called a neural network. It's a type of function. And we'll see why maybe this is another reasonable choice for a function and what's nice about it as opposed to the ones we've studied so far. Okay, so that's what you want to keep in mind. Neural network is just a special type of function. We're going to define it kind of slowly throughout this lecture, but maybe the best way to start is just through a visual like kind of representation of it. This is usually you'll see lots of pictures like this. And you should think of it like this, which is every function can just be thought of as like input on the left, output on the right. And we'll draw the linear and the sigmoid function in a similar way very soon. And so, okay, so we have our function it takes in as an input on the left. Remember, this was like x0, x1, x3. So here, in this case, we would have had, I guess I can write it, d was equal to 3. Right? Because you have x1, x2, x3. You have 3 dimensions for x, and then you have this x0 thing. So same as usual. There's this what is called we set it to 1. Okay, and then this is the output on the right. So it turns out this neural network, the way we're defining it, is the thing on the right is going to be the output, and information is going to be flowing from left to right. And there's some sort of procedure which I'll explain to you momentarily. Somehow this information from the input is flowing through these like connections all the way to the output in a special way. And formally, the way you would define this is through what is called a directed acyclic graph. So there's no cycles, and it's a directed graph. And so these would actually be like directed edges, but I'm not going to draw arrows for all these. But you should think of these all as directed edges that are flowing to the right. Okay, and so visually just keep this in mind, and we'll define it formally maybe in about 20 minutes. But for now, just like hopefully you can get a grasp of like the idea that information is flowing from left to right kind of. Okay, and then suppose we had this function. Well, what can we do? Well, we can just do what we've always been doing, which is run ERM for every procedure we've done and replace the function class with a neural network. Okay, and really that's what happens in practice, is that you will get a data set, This can be like pictures of cats and dogs, or pictures of lots of pictures in their labels, or lots of text on the internet, and then it would be like a sentence, and then what's the next word, or something like this. And then you need to, you define your learner to literally be the argmin in your function class, which is now going to be neural networks, that minimizes this empirical risk. And then you pick your loss function, which we've been doing. Nothing changes there. If you want to do regression style things, you'll probably pick squared loss. If you want to do classification things, they literally use cross entropy loss in like large language model stuff. Okay, so these are very applicable things. And the thing that they change is the function class is no longer these simple functions we've seen before, but they're neural networks. So these are the set of all functions such that f is a neural network. And here there's going to be some jargon, which we'll talk about later, which is neural networks with like some specific architecture. And that all that means visually is that you decide on like how many kind of what are called layers there are until the output, and how big these things are, like how many nodes do I put here, and so on. This is called like the architecture. And once you fix that, all that is left, we'll see, is to define these edges. And these edges are going to turn out to be exactly like these weights, these weight parameters we've talked about before. So once you define this architecture, what you're left with is a function class where every single function in the function class can be defined by a set of weight vectors, just like we've seen before, which is going to be beautiful because these weight vectors are going to be elements of like RD. There's going to be a bunch of them, but you can still do minimization as we've always done because they're just a bunch of multi-dimensional vectors. And so what you should think of is you have this function class that, once again, every function in it is what is called parametrized by what is now going to be a lot of weight matrices. Okay, so it's going to be a lot of weight vectors. But story stays the same as what we've seen. Okay, so hopefully this high-level view gives an idea of where we're going, and then all that's left is to fill in a lot of details of what this neural network function really is and why use it. Okay. So to start, before we even define it formally, I'm going to show you examples of neural networks we've already seen. So it turns out neural network is a generalization of many of the things we've seen. So for instance, let's start with the linear functions. We've used these to represent, our predictor for linear regression. And visually, as a neural network, this is what it would look like. And now you can get an idea of what these edges mean. So you have your input, right? D equals 3. And okay, well, we can write out some things. So like I was telling you that, the output of my neural network is going to be A. It's this thing on the right. And notice there's nothing in between. So you can have different neural networks that have different amounts of what are called layers. And you can also have different amounts of like what are called neurons in the middle. We'll define these terms a bit later. And the way this would work here is f of x has to equal to A, which we know must equal to like x transpose w, right? That's the definition. And we can expand this dot product and find that, oh, x transpose w, well, the definition of that, if d equals 3, is just x0, which is 1, times w0, plus x1 times w1, plus x2 times w2, plus x3 times w3. So I want to draw this visually. Well, it turns out this is like very natural, given what I had on the left, right? It's like, this is how it works. You have these inputs. You break up your input into its indices. And then these weights are just going to multiply the input. So you end up with an edge multiplying every input. So that's how these edges are working. So you take everything from the left of the edge and you multiply it by the corresponding weight. And then you get the corresponding output here. So this would be the corresponding weight vectors represented by all these edges, and it's routed to this single output neuron, is what it's called. Okay, that's where the neural network part comes from. These are going to be thought of as neurons. And good. So that's how this would be drawn as a neural network. Okay. There's one thing that's slightly missing, which we'll fill in just a moment. But first, let's try to address the sigmoid. What does the sigmoid look like? It turns out the picture is actually exactly the same. How is that possible? Well, let's see. So as I said, f of x is equal to A in a neural network. This is how it works. Okay, but we said we wanted to equal to this thing, the sigmoid. This was doing classification, right? We had this type of thing. Well, what's the definition of this? Well, let's just let's take the thing we've written already. That's just the decomposition of the dot product, right? And then you wrap the whole thing in a sigmoid. And that's all it is. Okay, but how does that work visually? Like this A now is this whole procedure. So what is A allowed to do? Like like now it has a sigmoid as well applied on these things. Is A allowed to like apply a sigmoid? And the answer is yes. These neurons in general will be functions of this form. What they will do is they will take the linear function of all the weights, like these edges, and multiply them with the corresponding inputs. So it takes a dot product with all of the previous inputs. And then afterward, it's going to be allowed to apply a function on top of this linear function. So this is a number, right? This linear dot product thing. And then it's allowed to apply a function on top of it. This is called the activation function. And it's usually a nonlinear function for reasons we'll see soon. And so in general, what you would write is that this neuron, which computes an activation, it'll apply an h, which we're going to call an activation function, on a linear function of all the previous inputs. Okay, so this is just to give you a sense. And so h here would equal to the sigmoid function, right? So you can write that. So h here equals to sigmoid. And above, we could also write it in this form. So we could also say like, oh, this above thing is also equal to h transpose w, but h here will just equal to, like, if you take in some z, it's just outputs z. So it's the identity. So if it takes in a z, it outputs the same thing. Okay. So that's how this neural network roughly works. It takes a linear function of all the previous things and applies an activation function on top of it. Okay, and we're going to see that this is how all of the neurons work in this neural network. Good. So before moving on to defining these things, let's think about why this type of structure would be useful, or what was also happening. Or actually, before getting there, there's another way we were doing things, which is we had polynomial features, right? How does that kind of visually look as a neural network? And this is getting more into the motivation. Well, what it kind of looks like is that you had some input x, right? And then you had a very specific procedure of transforming it into a new feature, a bigger feature. That was like a phi p function. So what you would do is, like, if, for instance, in this case, if you have p, you choose degree 2 polynomials, and you had 3-dimensional features, well, phi p would transform this, and yeah, it would transform this into what is, if you did the calculation, what ends up being 10 new features. So it has all of the new second-degree polynomial features, and that would be 6 of them, these 6 terms. So it creates a bunch of new features. And the nice thing is that some of these features might be useful to capture relationships you care about. So maybe, for instance, the relationship that is really important is the squared relationship of your input, because maybe something is growing as a squared function. And then you would really just care about this kind of feature, and that would be the important part for your output. And you can see for different problems, it's like, oh, hopefully you guessed right, and hopefully you created the right features. But if you needed a cubic growth, well, then you don't have that feature, and then you should probably use phi of 3 here. And then you end up with a giant new feature vector where maybe you would only be using the x, like x1 cubed term. So that seems like a little bit of a waste. But nonetheless, this procedure can be thought of as, after this deterministic mapping of this feature transformation, afterwards it is just a neural network, right, which is just this linear function in the same way we saw above, except now the input is not just x, it's phi p of x. And what the thing you should keep in mind is that this is like a like predetermined user-defined way of increasing the number of features you have somehow due to some prior knowledge, right? Where we're like, oh, for some reason, maybe the cubic polynomials are sufficient, or maybe the or the 4th order ones or something. Okay. And maybe not all the features are that important that you create. So in other words, the thing you should notice from this kind of example that maybe we haven't talked too much about before is that many of the new features here, so many of the new features in phi p, so many of these new features that you've created may not be useful. So you can end up only using like just one of the terms. And then you could end up with a lot of random terms that you didn't need at all. Okay, and so the observation is when P is large, this is very wasteful. And roughly speaking, the idea is, wouldn't it be great if we somehow define some sort of function that didn't, we didn't need to define how we're creating these features, but instead it somehow, learned what are the important kind of features that you would need inside the network somehow. Okay, and that's what the neural network is going to kind of do. Okay, let's see how that would look for a specific example, which is this is a classic kind of example that people will use to like understand how a neural network might learn useful features that you don't have to hard code or choose yourself. So here's the task, a very famous machine learning task, which is binary classification of whether there is a cat or not a cat in a photo. Okay, so the labels are not cat 0, 1 for cat. And the input is going to be your feature, which is a picture. Okay, here's an example of a picture. This is my drawing of a cat. So there is indeed a cat in this photo. And you'll get it like as a pixel image. Let's say a black and white pixel image, a 16 by 16 pixel image. And okay, maybe a little bit unrealistic, but the value of each pixel is a real number. Of course, this will be like some, maybe 16-bit binary number or something like this on your computer. But for the sake of an example, each pixel is somehow represented as a real number. And you're going to have how many pixel values? Well, 16 times 16, so 256. That's your dimension. And the way you're going to represent this photo as a vector, and we've seen this kind of before, is you just take either all the columns or all the rows, and you just stack them into a giant vector. So you end up with 256 pixel values. Okay. There's better ways to do this. We're not going to talk about it in this course, but for the purpose of this will work fine, just fine for simple examples. And you get your new feature vector, and the last thing is there's this x0, right, where x0 is always equal to 1. So we end up with 256 plus 1 dimensions. So far, everything's standard. And what we want to do is we're going to do binary classification in the way we've done before, which is we're going to, before we use the sigmoid to predict the probability of getting class 1. And then if it was over 50%, we would pick it, and otherwise we wouldn't. That's going to be the way, our predictor looks. So we're going to have a function, which is a neural network now, which is going to output as the final neuron the probability of a cat. And before, if we just used a really simple neural network like this, the sigmoid one, right, this was just the probability, right, the sigmoid function was just the probability of getting 1, of getting the label 1. Now we have a more complicated function. And so how should we think about this thing working? Well, without having these layers in between, right, just that sigmoid thing, this was simply a map from input to output directly with this linear and then sigmoid applied, and there was just the probability and so on. But now we have these things in the middle. And in this case, it's a very specific neural network that has 2 layers because there's 2 things in the middle. Well, actually, different people call it different things. In this course, we went with, well, we'll see. We'll call this a 3-layer neural network. And the version with the sigmoid was like it had 1 layer. It was just the output layer. So we have 3 layers here. So what are these these are called the hidden layers. What are they doing, or what can we think of them as doing? And one way to do that is just to, well, you can, input a bunch of pictures, and you can see for what pictures are these kind of like the largest values. So like for some pictures, this might be a really large number, and all the others might be small. While for other pictures, maybe this neuron, right, might take a really large value, but all the others are small. So we could wonder, like, what are the pictures for which this is really large or this is really large? Okay, and I should step back and mention one thing, which is similar to how we've been doing everything in this course. What I'm going to be talking about is what is going to happen, like what is this function going to look like after we've already done ERM? Like at the very end, you've done ERM, you've produced your predictor. How should you like interpret its behavior? Like what does it look like? What are these things inside doing? So it's already learned how to predict things well. How can we interpret like what it's doing inside? Okay. So the way we can interpret is, once again, you can look at each one of these what are called neurons, and we'll formally define them right after this. but they take on values. They're going to take values, and depending on the input, they're going to take different values. So we can just wonder what inputs make each one of these kind of the largest value. We can look at what do those inputs look like. And empirically, people have done this a bunch, and this is called kind of like interpretability research of neural networks, like what are they doing inside? And some of the simplest observations was things like, oh, one example maybe if I look at when this neuron is its largest value, like for what kind of inputs, you might find a picture. That's not a picture, so like this is your picture. And you might find that, oh, it's particularly the largest maybe when there's like a kind of edge like this. So maybe people will then say, oh, it's kind of recognizing, you know, an edge on the kind of the back of a cat or something like this. And then maybe you look at some other neuron, like this last one here, and well, there you might find that it's kind of takes on the largest values, where maybe not this edge, but maybe it's like these two lines over here, which, you know, I'm really over exaggerating, but like it's kind of maybe detecting the two lines which are the back two legs of a cat or something like this. And so these are like sort of simple things, but they're much, you know, much more kind of high level features or ideas of things than just the simple pixel values, right? So somehow we've moved so far from pixel values to like something a little more complicated, which is like edge detection, you know? So somehow these neurons might now represent the edges of the objects, and the edges particularly that we might care about. And then if we move to a deeper layer, like this one, and there's only 2 layers here, but you'll find even more complex kind of behavior. So you'll find that, oh, and this is once again empirically kind of verified, that you'll find that, oh, this thing might actually kind of recognize the head shape. So it's particularly, this one is the largest value when the inputs are like, take values here. Okay, and it doesn't really matter what else the other inputs take. It's just these are the most important things to make this the large. So maybe you'd be like, oh, this the you know, capturing this idea of a feature that's the head of a cat. And then you might look at another one, and maybe the other one catches kind of the feature that's like the torso of the cat or something. And of course, these are very simplified kind of views, but empirically, yeah, you find much more noisier looking ideas of this. But indeed, this is what you find. And what you would say is that, you know, at the beginning, the way this works is similar to everything we've seen before, you randomly initialize the weights. So when you randomly initialize the weights, that means these edges are all random. They mean nothing. But after doing ERM and producing your final predictor, what you will find is that these weights now get some meaning. And the meaning is that, as we have discussed, that these kind of neurons will have this interpretation. And so what you can think about is that these inner layers, these are called the hidden layers, are learning kind of useful feature representations. Whereas you get deeper through the layers, they're learning more and more like high-level abstract features that are useful to then finally make the final prediction. Okay, so hopefully that's enough of motivation of why this is like an interesting function class that people would use. And so what is left is to define the neural network formally, like what is the definition of the output based on the inputs? How does this actually work? And after that, what we will do is write out ERM a little bit more formally and then make a couple observations, and that'll be the end. Okay, so how does this work? So the way we're going to define it is we're going to start with a very, like a specific neural network, the one we've been studying, which has 3 layers, okay? So now I've added a lot of terminology in this picture. And afterwards, we'll consider the general case where you can have as many layers and as many neurons in each layer as you want. So first, we'll work with a specific example that has a specific number of layers, a specific number of neurons, and we'll define how are each one of these things calculated. And we'll just start from left to right and just write out the mathematical expressions for all these things. Okay, so some terminology, as we've said. Circles in these pictures are called neurons. And the lines are called the weights. And they connect neurons from the previous layer to neurons to the current layer. Each layer is numbered in the columns or layers. And within a layer, there's a certain number of neurons. So here, this would be like, you'd have 1, 2 neurons here, and this one above here is like this kind of bias neuron we've seen before, where it just is always set to 1, similar to how the input here was always set to 1, so that you can have these offsets. Okay, and some pictures will not draw these neurons, and they'll just do this, but mathematically they'll still use them. So this is how we're drawing it. And notice this has nothing, there's no connections to the previous layers here. This is simply so that when we write out the weights, which we'll see, these weight vectors, so that they multiply a constant one, so that they can have the similar offset we've been studying in this course. Okay, so I think that's enough explaining of the visual thing. So all that's left is to define what is this functions. How do we calculate them? So let's do that from left to right. So let's start with defining this thing. So we're grouping all of the neurons. So the neurons are like the circles, and the values they take we'll call as the activation of that neuron. Or the value of the neuron is the activation, it turns out. So we have this activation vector. The value of all these things. So what does it look like? So let's start with studying that first. So what is this A1 vector guy? Well, this A1 vector, the one is above. Oh, and just more notation. Superscripts will be used for layer numbers, right? So this is layer 1. These are layer 2. They all have 2. Layer 3. And subscripts, as before, we'll use for indexing within the current layer. So like for indexing this vector. So what does this look like? This looks, it's defined as activation at layer 1 at index 0, which is always equal to 1. Activation layer 1, index 1. Activation layer 1, index 2. Okay. These are all called activations. And how do we define each one of them? So A0, that was easy. The 0th index for each layer will just be 1. Except at the output, of course, because at the output it's not connected to anything. We'll see that. Okay. So how is A1 1 and A1 2 defined? Let's look. Well, A11 is going to have the following definition. So we saw that it should have this linear function of the previous activations, right? And so let's look. A11 is, well, it's going to be this linear function of all the previous inputs. And it's going to be weighted, this linear function, which uses these blue weights, okay? And then A12 is going to be also a linear function, but that uses a different set of weights, the green weights. So we end up with 2 linear functions, one for each of the corresponding activations. So in particular, we'll have that A11 is going to be a linear function of the previous activations, which are just the input, so that's just X. X transpose, and now we're going to use the blue weight vector, which we will denote as W vector 1 over. So 1 for the corresponding layer, because we'll have weight vectors at different layers, and then subscript 1 to denote it's for this index 1 activation. So layer 1 weight corresponding to activation 1 at layer 1. Okay, so that's that. And then we also saw that, well, this activation just applies a function on top of this linear function. So similar to how we've seen a sigmoid being applied, you can apply many other functions on top of this. So that will be H. And you can choose a different function for each layer. So this is sort of common. It's probably the most common to just use the same activation for every single neuron at all the layers and not change it up. Sometimes people might change the activations between layers, and it is extremely weird and uncommon to change the activations within the neurons within the same layer. So usually H is just like the same function throughout. Sometimes people will change it between layers. So that's why there's a 1 here indicating the layer. Okay, so that's, and an example of this, so this is called the activation function. And like one example was sigmoid. And we heard in last class, which we won't define right now, there's this other one called like the rectified linear unit. And then there's all sorts of other activation functions that people have come up with, which we won't study, but you can imagine there's a whole line of research of different functions that you can change, and then each of them have different behaviors, and you can study it, and so on and so on. Okay. But this is just to give you an introduction of like the different components that one could tinker with and could make changes. Okay. And we'll see why it's going to be useful to have this as a non-linear function very soon. Okay. Or in other words, why it's going to be very useful to not just have this as the identity function. Why not just have linear functions everywhere? Okay, so we'll see that. And then A12 is going to be, I mean, quite literally the same definition, and I'll just copy and paste it to show you which indices change, right? So still, where it's still layer 1, so this is the same. These 1 is still going to be the same. And then all that's going to change is this weight vector, now using the weight vector for, the second neuron. Good. And people will call, okay, so that's what that looks like. And it turns out that I wanted to use slightly different notation. So I'm going to just replace these, because people like to break this up into another term, and give it a variable name. So these inputs that go into the activation are sometimes called the pre-activations. And people will write that this input here is like Z1, 1, and this is Z1, 2. And this is what they're defined as. So that's all I've done. And people call these things your pre-activations, or the things that go into your activations. So these are called, these are pre-activations. But you can see these are just kind of fancy names for things we've really seen up to now. They're just the linear functions that go into the activation or the neuron that then get an activation applied to them. Okay, and good. So we're done basically with this layer. We've defined kind of this thing. Maybe one last sanity check is to check the dimensions of objects so that we're all on the sort of same page here. And another thing we'll sometimes use is that this, so to keep with notation and stuff like this, notice this is layer 1, so we use a 1 here. Layer 2, we use a 2 for these activations. And so for the 0th layer of the input, we'll sometimes also talk about this as these inputs are like the activations at layer 0. And we will sometimes use that x vector is equal to A0, which should make sense, right? Oh, it's here, this thing. So you could have just as easily replaced these x's with A0. Okay, so let's look at dimensions. So like this A0 vector, well, its dimension is, as we saw, it's just R of D plus 1. This is the usual dimension of the input, right? What is the dimension of the weights? Well, the weights at a current layer must match the dimension of the previous activations, right? Because it's a dot product with the previous thing. So, and what you will be hopefully noticing, and you will find when you work on neural networks in the future and in the next assignment, and even in the softmax multi-class things, is that half of machine learning is making sure your dimensions match. And if your dimensions match, then most of the time you're in good place. So like a lot of time for debugging, just like a tip is it's very useful to just print the shapes or the dimensions of objects in your code to make sure that they match. Okay, and so what are these? These are also in R of D plus 1. And then finally, this activation. Well, what is this thing an element of? Well, this thing is an element of, well, however many neurons we chose to have in that layer, plus 1. So it would be written as, and we'll have a variable for this later, but it'll be written as like 2 plus 1. Number of dimensions, number of neurons you pick for a layer, plus 1. Okay, and now to speed things up, we just need to define A2, and A2 is defined in basically the exact same way. So let's just copy and paste a bunch of things and do that. So A2 will be like this. What do we change? Well, we're changing 1 to 2, 1 to 2, 1 to 2, 1 to 2. Lucky enough, there's exactly 2 neurons here. Oh, so you really don't need to change much. And then A1 becomes 2. Activation becomes at layer 2, pre-activations at layer 2, and so on. So all the same patterns for all the layers. And the pre-activations are defined in the same way as well. And now we'll change the x to using the activations at the previous layers, right? So it'll be Z2. And what we'll need to change is this x. It's not x anymore. Visually, we can see what it is. It's, well, what's coming into this neuron? What's coming in is all the previous activations. So we use this activation vector, dot producted with this blue set of weights. So it's activation vector at previous layer, so layer 1, the vector, dot producted, so you take its transpose with the weight vector at the current layer, which is layer 2. Okay. And that's the same, but and you replace, what's going to replace here? Well, it's going to be not the weight vector for the first neuron, but for the second one. Okay, good. And then we can quickly just do the dimensions of things. So all that we need to check here is what are the dimensions of the weight vectors at layer 2. Notice that the weight vectors will always all be the same dimension at a particular layer. And if we look at it, what is its dimension going to be? Well, it's going to be the number of neurons at the previous layer, including this bias neuron. So that's just 3. So these should match the dimension of the previous activations. So that's just R of 2 plus 1. And the new activation, A2, is also an element of R2 plus 1, because there's 2 neurons. There's 2 neurons plus this bias. And now we get to the final layer, which just has a single neuron. And what is its definition? How did I write it? Yeah, there's A3. We could have just as easily, to keep the notation, wrote like A31, but doesn't matter. So you have A3, and this guy is going to be defined in the same way. So it's going to have its own activation, H3, and that's going to be applied to a Z3. And the Z3 is going to be in the exact same way as before, which is it's just going to be equal to, and I can take this equation, and you use the activation from layer 2, and you multiply it by the weight vector at layer 3 now. And that would correspond to this set of weights here. Okay, so that was like a nice slow step through these neural network, and the only thing that changes for the general case is that there's a different number of neurons, potentially, or a different number of layers. Okay, is there any questions? Oh, and we can finally check the last set of dimensions, which is that what is W1 at or W3? Well, W3 is equal to, it's always helpful to just visually look at it, but it's going to be the dimension of the previous activation. So there's 3 lines, so it's in R3, right? It's in R3, so R2 plus 1, you should think of it. And notice that the final activation is in R, and that the final output activation has no bias, has none of this equal to 1 term, because this term was only put here so that the weights that are going to be used to multiply it for the future layer can multiply a term that's a constant that you can shift. So since there's no further layer here, you don't need a bias term. That's the only difference. Okay. Good. Okay, so what happens now is that in general, a neural network will look like this, which is that it can have up to, you can have layer 1, layer B minus, up, all the way up to layer capital B minus 1, up to layer B. And we use capital B because capital L was already used for the risk. So B is the number of layers. And so that's a choice by the designer of the function class. The more layers, the more things you can represent, and it's going to have the same bias variance kind of style trade-off in theory as we've seen before. Okay. So that's how you should think about it. Like more layers means more complex function class. You can represent more complex things. And you can also have some arbitrary number of neurons at each layer. So, and we're going to use for that d to the power of this brackets layer number. So the number of neurons here is d to the 1. The number of neurons here is d to the b minus 1. And in general, you can have some multiple output neurons. You don't have to just output a single number. You can output multiple things. So if you want to do like multi-class classification, you can output k different neurons here. Okay, and so let's just quickly step through how this looks. So if we pick, like, all we're going to do is just pick a particular layer, B, from any one of these layers. And all I'm going to do is write out its equation in general, which is essentially just a generalization of what we saw before. It's like it's going to be the same thing, basically. So if you pick a layer, you're going to have some number of weight vectors. So let's pick some layer B. Let's say B was equal to 1. So I'll keep referring to layer 1. How is it going to look like? Well, the number of weight vectors there is going to be the same number of neurons as you have. So how many neurons? We're going to have D to the 1 neurons. And for each one, you're going to have this like weight vector that connects to every single thing in the previous layer. Okay, so then you're going to have a weight vector at layer B for the first neuron and for the second neuron, and up to a weight vector at layer B up to the final neuron. How many neurons is there? Well, there's D to the B. And so this D to the B thing, I'm just going to write it here, is D to the little b is equal to number of neurons at layer B. Right. Well, that's how many weight vectors you have. And each one of these weight vectors is going to be in R of, well, it has to do a dot product with the previous layer, right? So it should be R of dimension of previous layer. So dimension of previous layer, so that's B minus 1. And then you add a plus 1 for the bias. That's it. So all it's saying is that, yes, I have a weight vector for each neuron. The number of components it has is just, it needs to do a dot product with the previous layer, so that better match. So you can see how important all this dimension matching becomes. The pre-activations are also quite simple. You're going to have these Z of B for your layer, and you're just going to have one pre-activation for every single neuron, right? How do you compute each one of these activations? Well, you first calculate its pre-activation. How many pre-activations are there? Well, as many as there is activations or neurons. So, okay, there's going to be a Z B of 1 up to Z B of D to the B. Okay, that's your vector, and it's an element of R, R to the D B, right? This is the number of neurons here, so that's what that is. And each one of these is just going to be defined as the linear function or a dot product of the previous activations, right? So each one of these, Z, we'll call it ZJs. So for any J, which is a number between 1 to this, it's equal to, right, we're going to do this dot product with the previous layer's activation. So we're going to take the activation from the previous layer. What's the previous layer? Well, that's B minus 1. We're going to take that vector, take its transpose and dot producted with the weight vector at the current layer. But for neuron number J. Okay. So this is for J element of so for every neuron at the current layer, what is your current pre-activation? Well, it's just the dot product with all the activation vector of the previous layer. And then the activation has a few cases, just to make things very clear. So for the input, we'll call, as we've seen, we'll call this like activation value to the 0 equal to X. That's just the input. Well, that's going to be R of D plus 1. And we're also going to use the terminology that D of 0, right, which is like the number of neurons at layer 0, is of course just equal to D, just to keep this kind of notation unified. And so then this will also be equal, this R of D plus 1 is the same as R of D of 0 plus 1, right? Okay, so with this notation in mind, what you will find is that the activations for all the layers except the last one will be of the same form in the sense that they have this bias, okay? So all the activations for layer B will look like A, B, so neuron layer B, 0, index 0 is always set to 1, except for at the last layer. We'll define this in a second. And after that, you have these A1, B2, and I'll define these just below. Up to, so how many neurons do we have? Well, we have D to the B neurons, or activations. This is, of course, an element of our number of neurons plus 1. And this holds for all little b except for the last layer. So all b except for capital B, because at the last layer, you're not going to have this. So at the last layer, I'll just replace this with this special case where I replace little b with capital B. I remove this thing. And all these b's become capital B's. And there's no plus 1 anymore because we've removed that bias term. And finally, what is the definition of each of these? Well, it's as you would obviously expect. It's just, apply your activation function to the pre-activation function, or the pre-activation value, which you just computed above. So A, B of J, right? So activation of neuron J at layer B is equal to activation function at layer B applied to pre-activation at layer B of neuron J. And I'm just making this very clear, but the that like how important. Okay, this is just a number. That's not that interesting, and that's for J from 1 to number of neurons in that layer, which we have seen is just D to the B. Okay. And the reason we write all these things is because really to emphasize how important the dimensions are. Like a lot of this is like you can figure out if you're correct about a lot of their neural network stuff if the dimensions match. And so this is very helpful to check dimensions of everything. Okay, and then finally, the last thing is there's an activation function for each layer. We call that H of B. That's just a function from, how does it work? Takes in as input a number, right? Because what are these pre-activations? These pre-activations are dot products. A dot product gives you a number. So it's a function from the real numbers to the reals. That's what it will be. And we'll put here is that usually nonlinear. Okay. Nonlinear function. And so then finally, the way this works is that your neural network function you should think of as a function that takes in some input and produces an output A of B vector. Okay, that's really the takeaway, and it's through this whole like layered, procedure that we've described. Okay, and good. And so now we can finally understand what it means to have a neural network architecture. So there's a bunch of things you need to define a neural network, right? Let's just look at them. You need to define the number of layers B. You need to define the number of neurons in each layer. You also need to define the activation function you're using. And then you need to finally define what is the value of every single weight vector here. Once you have that, if you give me all those, I can compute to you for any input the output. I can just go through this procedure and give you the output. It turns out that if you give me everything other than the weights, what I have is like kind of the structure of the neural network, except I don't have values for the edges, right? That's what the weights really give me, is values for the edges. So what people will call this is a neural network architecture. And in other words, it's like a kind of a fixed neural network structure. It's a fixed graph with the only thing missing is the weights. And for each set of weights, you'll get a different neural network. And so you can think of that as defining a class of functions. It's the class of functions that all have this type of neural network architecture. And okay, so just to be clear, defining the number of layers B, the number of neurons in each layer, all these, and the activation functions, these, that will give you what is called the neural network architecture. And we'll see that that is going to be how that function class is defined, right? It's going to be the set of all functions with a fixed neural network architecture, which you pick beforehand. And the thing you're searching over is different values of the edges, which are the weights. Okay, good. And let's just move on here. So before defining this kind of formally in the ERM thing, we need to simplify notation a little bit because there's a lot of weight vectors, right? There's like a lot of weight vectors in each layer, and then there's a bunch of layers. So we're going to kind of group all the weight vectors in a single layer into a matrix. And so we're going to have as many matrices as there is layers. And so that's the idea. So take all the weight vectors at a particular layer B. There's d to the b of them, and you put them in a matrix. You stack them as columns. And so now if you remember what, like, visually what it would look like if you had like an activation at b minus 1, I guess, a vector, you should think of it as like, you know, this row vector. It kind of looked like this. And you would multiply it with this column vector, which would have been like w b, and then you pick whichever neuron you want, j. Well, all we've done is we've just stacked a bunch of columns. And if you remember the way matrix multiplication works, is if you multiply, you know, a row vector by a matrix, it's the same thing as taking that row vector and then applying this dot product and this dot product and this one up to there. And so it turns out that one way to compute the new activation is just going to be to take the activation of the previous layer like this, right? So this is really this thing transposed. And multiplying it by this weight matrix. That will give you the full vector all at once. And then you apply the activation function. But now you're applying it to a vector of all these things. And so the way we interpret this is this activation function, when applied to a vector, is just element-wise application to each index. So it's like, it just means apply this thing to each of the indices, right? That's a notation. And with that notation, we can now kind of view the neural network thing as one function I can write on one line, which is why I wanted to do this. So you can write f of x, right, which is equal to the final activation vector at the final layer. What is this equal to? Well, it's like this giant kind of onion of operations, or it's called like the composition of a bunch of functions. So it starts all the way at the beginning, right? It's like I take my input, and I take its transpose, and I multiply it by the very first weight matrix, right? Weight matrix at layer 1. That's how it all begins. Once I get that, I get a bunch of pre-activations doing this, and then I will apply my activation function at layer 1. And this gives me all the activations at layer 1. What do I do after that? I then multiply all those activations by the weight matrix at layer 2. And what does this give me? Let me just maybe make this clear. What is this? This thing was called A1, right? So very nice. This looks exactly like the activations of the previous layer times this, right? And so that's looking good. And after that, I need to apply another activation function, h of 2. And then you repeat this process over and over again. And so I'll just put like dot, dot, dot. You eventually get to the weight matrix at layer b minus 1, capital B minus 1, and then eventually to the weight matrix at capital B. Okay. Oh, one last thing is this thing, of course, this whole thing, when multiplying it by the weight, oh, actually, it's already a row vector, so it's all okay. Okay, good. And so you do that whole thing, and on the left, what you end up with is like dot, 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 and then you would eventually apply the activation function at layer, the second last layer, and then the activation function at the last layer. All right, so you do this whole procedure, and then you get your final output. And so you can see it's just a composition of a bunch of operations. And then you can see, okay, what happens if this h was a linear function? Or a very simple example of a linear function is just if it's the identity function. And this is where we see why a nonlinear activation function is very important. So if h of b for some input z was just always equal to z, so it's the identity, it's called the identity function. Well, then if you look at the above operation, well, then f of x will just end up being x transpose times w1. This is not that this thing just passes it through, times w2. h2 just passes it through. It's the identity, and so on. And so you end up with this thing, which is x transpose times w1 times w2 times w3, all the way up to wb. And if you remember in linear algebra, if you have a bunch of matrices multiplying each other, you can always represent that as a single matrix. And so you end up with X transpose W, where W is the matrix you get from multiplying all these together. And so that's kind of disappointing because what we ended up with is, okay, well, first of all, what is this matrix an element of? It's an element of, and so, okay, people write matrices that, like, we haven't really covered this, but you first write in the superscript of, and this is really, this notation is not formally defined at any point in this course, I guess, but you'll write the number of rows first, which would be d plus 1 rows, right? Because the number of rows should match the size of the size of this row vector. And then the number of columns can be arbitrary, but the number of columns here is going to be the number of output neurons. So you'd write this little x, and it really means the Cartesian product in the power of the number, which means probably nothing, other than it visually somehow makes sense. But we won't cover that. And so the number here is going to be d to the b. Okay. That's how that works. And I guess I don't need brackets. But that's just emphasize that this is a matrix with this many rows, this many columns, and it'll produce, this whole thing will become an element of our d to the b. And so all you really end up with is this solution, which looks like, what does it look like? Well, first of all, this is just d to the b linear functions, which is kind of disappointing because we could have represented this without any of this neural network stuff. And it's really what we've seen for this multi-class kind of setting, which is it's the same type of thing you get when you do multi-output regression. So all you learned is a linear, you learned d to the b weight vectors that are applied to that many linear functions. So you learned that many linear functions, which was not that exciting at the end of the day. So that's why non-linearities are very useful, because you actually get some more interesting behavior other than just learning this many linear functions. Okay, so you would pick, so a sigmoid is like a non-linear function. And then what does the procedure finally look like? Well, it looks like this. You do ERM with neural networks, and we saw this at the start of class, but well, now it can be defined a little more formally. You have a data set. That's all the same. Your learner is also the same. It's just ERM. It's you output of hat, which is the minimizer of the empirical risk. Empirical risk defined in the same way. Pick any loss function you want. Now this function class hopefully makes more sense. It's a set of all functions that are neural networks with a fixed architecture. And if you recall, when you fix the architecture, what you have is this directed graph with everything defined other than the weights, which are the values of the edges of this neural network. And so every single function in here is defined by b weight matrices. And so we'll write them as like f of w1 up to wb. Depends on these weight matrices. If you change the matrix, you might get a different function. And so finally, a little more, like, I guess, explicitly, what it looks like is that this f hat is just a vector b, which is like this, the activations at the final layer of your neural network. And how is this thing defined? And it's defined because f hat is based on some weight vectors. What weight vectors is it going to be based on? Well, it's going to be based on, remember, we used to write that f hat was based on a w hat vector. Well, now it's a w hat matrix, and you actually have a different matrix for every single layer. And so you had to learn these through ERM. And then how did you, like, what does that mean? It means that you've actually chosen the weight matrices, right? So these W1 up to, and I'm not going to write their dimensions because that'll be a little bit ugly. And that's going to minimize the empirical risk of this function of the function class. So I can write it in here. So I was just picking essentially the best set of weights in the sense that they minimize the empirical risk. Or in other words, a set of weights that can best label your data, right? And just to be clear, this notation now just means L hat oh, I guess, sorry, I'm going to define this notation. So this, we already know what this means. I'm just going to simplify it for the be the following. So if I pass in just weight vectors, it means, plug it into the neural network. Okay, and then finally, there's no closed form solution usually, unless you've picked like, the identity function and picked the right loss. So usually no closed form solution. And so here, what everyone really does is they run gradient descent. And we know how to do that. What does it look like? Well, it's like, there's a bunch of weight matrices, and each one of them is built up of a bunch of weight vectors. And so you're going to do it for every single weight vector in your neural network simultaneously. So similar for softmax, remember you did it for all k classes. Well, now you're going to do it for all the neurons, for all the layers at each epoch. So at each step, at each iteration, you're going to update all of them at once. So it'll just look like if I take a weight vector at some layer b and at some index, like some neuron number j, then its t plus 1th iteration will equal to that same weight vector at its tth iteration, right? This is just gradient descent, minus a step size. And now this is where the notation is going to be useful. So the gradient with respect to this vector, we've seen what that means before of, well, it's exactly like I'll just copy and paste. It's exactly this empirical risk, right? So we're taking the gradient of this empirical risk. However, what we're plugging in is the weight matrices, right? At what time step? Well, at the previous time step. Okay, and so what that looks like is this kind of ugly notation where you take this weight matrix at time step t and this matrix at time step t, which is just the weight matrix at the previous time step, plug that into your empirical risk, and then take the gradients. And this has a famous name. Okay, well, first, B, right? It's the, what's B? B is any layer. So you do this for all your layers, 1, 2, capital B. And J is just neuron number. So neuron would be from 0 until D to B minus 1. Because there's no, right, the number of indices of a weight vector depends on the number of activations before. So that's why this goes to dB minus 1. Okay, and this has a famous name, which is the procedure of doing this, which you won't do in this class, but really it's just applying like gradient descent, writing out all these formulas and a bunch of chain rules. And this procedure of writing all these chain rules, what you'll find is that the way you're going to want to write these chain rules is in a backwards way. So first you'll check how are these weights affected by the loss, and then how are these weights like the weights here affected by these weights, and so on. And this idea is like you're kind of computing this chain rule backwards, and people call this backpropagation. So however you spell backpropagation, maybe it's like this. So backpropagation is the method of computing this gradient. And you would do this update for all the B's and all the J's, and there's on your computer, like in these machine learning libraries, they just do this for you, and you don't have to manually compute all this stuff. So you just tell it the loss in your function class, and it'll do it for you. And I leave you with this wonderful note, which is that if we look at this function, this empirical risk that we are minimizing, everything seemed really good up to now, right? Which is that we're minimizing this function. We got this better function class in some way. It's learning these features in some like nice procedure. But what happens is this function we're minimizing is usually, for the first time, not convex. And so we really can't ensure that we're getting to any sort of global minimum. And visually what that would mean is if you had like a plot in 1D, which is of course not in 1D of L hat, and some reason you had a weight vector with 1 dimension or something, well, you might have a function that looks like this. And so this would be your empirical risk, and really you want to find this point, but it has a local minimum here. And yeah, this would be the point you end up solving for, unfortunately, with gradient descent, which is unfortunate. And how to resolve this problem is all left for future classes. And so that's kind of where we end the story here. And I'll, I guess, see you all virtually next week. Thank you.